Until now we have discussed about the TTL family, transistor logic. Now we are discussing how to design NAND gate by using CMOS technology. CMOS is nothing but complementary metal oxide semiconductor field effect transistor. In short, it is called as CMOS. In this CMOS, we use both PMOS and NMOS. P-channel MOSFET and N-channel MOSFET. Here, all the MOSFETs we are using are enhancement MOSFETs. These are P-channel enhancement MOSFETs. These are N-channel enhancement MOSFETs. The arrow direction in the PMOS is pointing to the right side and the arrow direction in the NMOS is pointing to the left side. As you already know, these two are source and drain terminals and this is a gate terminal. This is source and drain gate terminal. We always give the supply to the gate terminal only. If you remember the PMOS operation, if we give the 5 volt supply to the PMOS, here the substrate in the PMOS is N, P plus. If we give the 5 volts to the PMOS, then negative voltage is induced on the other side, which is reducing the number of holes that are reaching from source to drain, thereby turning it off. So when we give the plus 5 volts P-channel MOSFET, PMOS is turned off. When we give the 0 volts or when we give 0, digital logic 0, the PMOS will be in on position. Similarly, when we give the plus 5 volts, NMOS will be in on condition. Now in NMOS, this is N plus, this is N plus, and the channel is P. Because we have given 5 volts, negative voltage is induced, so there is a chance for more number of electrons to reach from source to drain. So NMOSFET is in on condition. When we give the 5 volts to the NMOSFET, it is in on condition. When we give the 0 volts to the PMOSFET, it is in on condition. We use this concept here. These two are P-channel MOSFETs, enhancement MOSFETs. These two are N-channel enhancement MOSFETs. For the depletion MOSFET, we do not have these breaks. These breaks are indicating these are enhancement MOSFETs. I am giving the input to the gate. This is the truth table of the NAND gate. If both inputs are 0, then output is 1. If any one input is 0, then also output is 1. If both inputs are 1, then output is 0. Now initially, we are giving both inputs 0. Because it is difficult to understand by seeing the complicated MOSFETs diagram, simply we are representing them with the switching actions. Because these are working like switches. They are either in on condition or in off condition. Okay. Now I have taken the VCC. Instead of the transistor T2, I represented with a switching action. I am representing here a switch. Here also I am representing a switch. T3, here also I am representing switch. T4, here also I am representing a switch. Now we have connected the A to the transistor T1 and to the transistor T4. Input A. And we have connected B to the transistor 3 and transistor 2. First, initially 0, 0. Input A is 0 and input B is 0. If we give the 0 volts to the PMOS, it will be in on condition. Because it is in on condition, now it is short circuited. And B is also 0. So this is also in on condition. This is short circuited. Now to the NMOSFET, we have given 0. NMOSFET 0 means it is in off condition. It is in off condition. Now it is in off condition. Again, it is in off condition. We have given 0, 0, A, B. Both P-channel MOSFETs are in on condition and both N-channel MOSFETs are in off condition. Now what is the output Y? Output is VCC, which is nothing but digital logic 1. So first 0, 0, 1. When we give the both inputs, output is 1. This is verified. Now we are verifying what if we give A 0 and B 1. A is 0 and B is 1. When A is 0, for the P-channel MOSFET is in on condition and N-channel MOSFET is in off condition. Now this is in on condition, this is in off condition. Now B is 1. 1 means P-channel MOSFET is in off condition and N-channel MOSFET is in on condition. P-channel MOSFET off condition, N-channel MOSFET on condition. Because this is off, there is no chance to short circuit here. Only this is in on condition. Even though it is in off condition, VCC will reach to the Y in this path. So still the output is 5 volts or VCC. So digital logic 1. Even though we may call with different names, VCC, 5 volts, digital logic 1, all are same. Next we are checking, if we give the A is equal to 1 and B equal to 0, if A is equal to 1, for P-channel MOSFET it is in off condition and N-channel MOSFET is in on condition. N-channel MOSFET A is in on condition, P-channel MOSFET A is in off condition. Next, if we give the B equal to 0, P-channel MOSFET is in on condition, N-channel MOSFET is in off condition. So P-channel MOSFET is in on condition, N-channel MOSFET is in off condition. Okay. Now, what is the output? Again VCC is short circuited, output is 1. If both inputs are 1, 1, if both inputs are 1, 1, for 1, 5 volts, P-channel MOSFET, PMOS off and NMOS on. PMOS off, NMOS on. Because both PMOS are in off condition and both NMOS are in on condition, the output Y equal to 0. So NAND gate truth table is verified. So CMOS NAND gate has an advantage with the power. It consumes only less amount of power compared to the TTL and ECL. But the propagation delay of CMOS is higher compared to ECL and TTL. What is the advantage of CMOS? Why we are going for the CMOS? CMOS is giving the chance to consumption of the power consumption is very low. Out of all logic families, which logic family power consumption is low? In CMOS. Okay. It also gives the high fan out capability. So we can connect the output to more number of loads compared to remaining families, either ECL or TTL. Okay. So see what is the advantage of CMOS? The power consumption is very low. Disadvantage is propagation delay is high. Fan out for the CMOS is high or low? Fan out is high. Okay.